start the Tuesday morning session. So the first speaker is John Ellis from King's College London, who will be telling us about particle physics beyond the standard model.
Okay, thank you very much. So it's always a pleasure to be back here in Bogota. And so here I have this sort of image which sort of describes the quest that we particle physicists have, looking for something on the possibly distant horizon beyond the standard model. So I have a habit of asking the audience to guess where this picture was taken. So I look forward to getting some answers at the end of the talk. So anyway, our quest for physics beyond the standard model is largely guided by this guy here. So here you have a picture of Peter Higgs back in 1965 when he was working out some of the details of his theory of the Higgs boson. So of course, as you know, the Higgs boson was discovered 5 years ago now, and we're still looking very closely at this particle to see whether there's any hints there of physics beyond the standard model. And that's one of the themes that I'm going to be discussing in this talk. So, just to remind perhaps the students in the audience, here we have a summary of the standard model. So we've got the leptons, we've got the quarks, and this is the Lagrangian, which fits on a t-shirt. So you've got the gauge interactions here, you've got the interactions with the standard metal fermions here, and the two bottom lines, those are the pieces which involve the Higgs boson. And of course, those two bottom lines were not checked directly until 2012. The two upper lines of the Lagrangian have been checked in great detail in experiments dating back to the 1980s, but the two bottom lines, the first direct evidence came in 2012. So, what did we expect for the Higgs boson? So, if you go back to the early papers of Higgs in 1966, the one that he was working on that first slide, and Weinberg in 1967, they wrote out what, according to the standard model, should be the couplings of the Higgs boson to fermions and to massive vector bosons. And of course we're still checking to see whether those predictions are correct and looking for small deviations that might be indicative of physics beyond the standard model. And, as I already mentioned, it's a theme I'll be coming back to later on. So my own personal interest in the Higgs boson started around 1975 when, together with Mary Gaillard and Dimitri Nanopoulos, we wrote what I think was the first systematic survey of what a Higgs boson might look like. I think at that time the number of papers on the Higgs boson phenomenology could be counted on the fingers of one hand. And the distinguished senior professors sitting in the front row regarded all this stuff as being extremely speculative. And that's one of the reasons why at the end of our paper we wrote that we do not want to encourage big experimental searches for the Higgs boson, but we do feel that experimentalists might like to know what it looks like. So, fortunately, of course, our advice was not taken by our experimental colleagues. So, the first workshop on LHC physics was held in Lausanne and CERN in 1984, and I got the job of reviewing the physics that you might look for at the LHC. And so one of the things that we discussed together with Graciela Gelmini and Henryk Kowalski was the production of the Higgs boson. So here you see some of the cross-sections for producing the Higgs boson. One of the other things that we discussed was supersymmetry. I'll come back to supersymmetry later in the talk. Okay, so continuing to focus on the Higgs boson, of course, since 1984, a tremendous amount of work has been put into figuring out what a Higgs boson would look like at the LHC. And here you see the latest predictions from the LHC Higgs cross-section working group, who to put together all the available theoretical calculations of the Higgs production cross-section as a function of the mass of the Higgs boson. So the different colours here refer to different production mechanisms. I'm not quite sure whether you can make them out. The dominant mechanism is glue-glue fusion to produce a Higgs boson. That's the blue one up here. Then there's a couple of processes involving massive vector bosons. There's vector boson fusion, where the incoming protons radiate Ws, which produce a Higgs. And then there's a process where you can produce a Higgs boson in association with a massive vector boson. That's the green one. And then here, in sort of pink and purple colours, are other interesting mechanisms where the Higgs is produced in association with a top quark. So if, just say, the mass of the Higgs boson had been perhaps 750 GeV, then the cross-sections would have been very small, and it would be difficult to measure many of them. But we're lucky. Higgs boson weighs about 125 GeV, and we can hope to measure all of these mechanisms and probe to see whether the standard model really works, or whether there's some physics beyond the standard model. So, again, for the benefit of the students in the audience, here are some pictures of the main LHC detectors while they were under construction. Of course, the ones that discovered the Higgs boson and are now looking for supersymmetry in dark matter are Atlas and CMS. Columbia has been participating in those experiments for over a decade now, but it is also now participating in the two other major experiments. Very glad to see the way in which the Colombian experimental community has grown over the past decade. Okay, so let's now look at what those experiments have actually measured. So this is actually a compilation slide from Atlas. CMS has something very similar. And what you see here compared are the theoretical predictions with the experimental measurements. And what you see is that all these measurements are consistent with the theoretical predictions. I'm sure that you'll hear more about that in detail from later experimental talks. And among those cross-sections are the cross-sections for producing the Higgs boson. And you see here again good agreement between theory and experiment. So on the one hand, theorists could be happy. On the one hand, I think we should all be unhappy. We would be much more excited if there had been some significant deviation from at least some of the standard model predictions. But so far, that's not the case. Okay, so the Higgs boson has been discovered, it's been measured, and in particular, the mass has been measured. And this is from a joint Atlas and CMS analysis, measuring the mass with the run 1 data at 7 and 8 TeV. And you can see the mass is already known with a precision of something like 2 per mil. In fact, both Atlas and CMS have come up with updated measurements with their more recent data at 13 TeV. For example, there's this measurement from CMS just in one channel alone, which already has a smaller error. So you might ask, well, what's so interesting about measuring the Higgs boson mass with high precision? Well, of course, one thing is that it enables you to make precision tests of the standard model and do precision probes of physics beyond the standard model. Another reason why it's very important is because it's actually crucial for the future of the universe. So here it's written in more technical terms, crucial for the stability of the electroweak vacuum. So let me explain this point in a bit more detail. So we saw back on the first slide the Lagrangian for the standard model. It includes a Higgs potential. That Higgs potential includes a coupling, a self-coupling of the Higgs boson. Now that self-coupling of the Higgs boson, like any other coupling in a quantum field theory, is subject to renormalization effects. And in particular, that self-coupling renormalizes itself. And that self-renormalization tends to increase the Higgs coupling as you go to higher scales. However, in the standard model, with the measured values of m Higgs and m top, that is not the dominant renormalization effect. The dominant renormalization effect is actually due to the top quark. You can see here, this is very sensitive to the mass of the top, and if the top mass is large, as we know it is, this effect dominates over the renormalization by the Higgs itself. So this is one plot of this effect, which shows that what it does is that it drives the Higgs self-coupling negative when you go to high scales. That means that the electroweak vacuum, empty space, is formally unstable. And I'll discuss this point in a bit more detail on the next slide. Now, some people say they don't care about the instability of the vacuum. Personally, I do care, and I believe there must be some new physics which comes in to prevent the vacuum from collapsing. And one possibility for that is supersymmetry, which I'll again return to later on. So let's discuss this in a little bit more detail. So here we have a cross-section through the Higgs potential that we're reasonably familiar with. This is the so-called bottom of the wine bottle part of the potential. And naively, you would think that the sides of the wine bottle go up indefinitely. But in fact, no, because of this renormalization by the top quark, it turns down, and that induces an instability. So this is taken from one of the most recent calculations of that instability effect. So these ellipses here represent the current experimental uncertainties in m Higgs and m top. And this is the stable region down here. So the best available measurements indicate that we're not in the stable region, we're in this unstable region. Well, when I say unstable, the lifetime of the vacuum is long. It's much longer than the age of the universe. So that's why some people don't worry about it too much. And probably we should all worry about Donald Trump destroying us in a nuclear war rather than the fate of the vacuum. So the principal uncertainties are those due to the measurement of m Higgs and m top, although there is also an important uncertainty from a strong coupling constant, alpha s. And all of this is summarized in this little formula here, taken from a paper by Brutazzo et al. And it indicates that the instability scale is somewhere around 10 to the 10 GeV. So my interpretation of this is that it's telling us that there has to be some new physics beyond the standard model at a scale below 10 to the 10 GeV, which can avert this instability. Now, unfortunately, 10 to the 10 GeV is above a TeV. So this argument does not tell you that you're going to guaranteed to find that new physics at the LHC, although, of course, you might. So as I mentioned, I believe that we need new physics to stabilize the vacuum. And together with Douglas Ross, a number of years ago, we looked at this, and we said to ourselves, well, look, the dominant destabilization effect is due to the top quark, the fermion. So let's put in a boson to cancel it out. And so you can do that, that works. You have to put it in, of course, below that scale of 10 to the 10 GeV that I mentioned, but you can do that. The trouble is that when you do that, if you introduce an additional scalar field, you introduce additional scalar couplings, which can also be unstable. They can also cause a collapse or a blow-up. And in order to stabilize those other scalar couplings, you introduce other fermions, and by this time, you've constructed a theory which looks rather like supersymmetry. Okay, so that's the issues beyond the standard model that are posed by the measurement of the Higgs mass. Of course, the experiments have also measured Higgs decays. So this plot here shows you the expected decays as a function of the mass. And again, the fact that the mass is around 125 GeV means that many of these decay modes are accessible. Now what's interesting, and perhaps ironic, is that the dominant production mechanisms for the Higgs boson and one of the most prominent decay modes for the Higgs boson, namely glue-glue production of the Higgs and Higgs into gamma-gamma, are actually quantum loop effects. They're not things that you find naively when you write down the Lagrangian. They're things that you only find when you do quantum calculations. And what that means is, of course, that right from the get-go, looking at the properties of the Higgs boson, we've been able to measure quantum effects which might be particularly sensitive to physics beyond the standard model. Okay, so specifically for a mass of 125 GeV, what do we expect for the Higgs decay modes? Well, the dominant decay mode is actually Higgs into BB bar. The decay modes which I showed on previous slides, which were Higgs into gamma-gamma and Higgs into ZZ star into 4 leptons, those are actually very small branching ratios. And the work is still there for the experimentalists to discover at the expected, hoped for 5 sigma level, all these different decay modes. So this is a compilation of results from LHC run 1. So they're grouped according to Higgs production mechanism, and then for each production mechanism decay modes. And you can see that for the dominant Higgs production mechanism, namely glue-glue fusion, there have been a lot of relatively accurate measurements. Some of these other production mechanisms, the decays are not so obvious. Now, the run 1 results did not provide the hoped for 5 sigma discovery of Higgs into BB bar. So that's one thing that we hope to get from run 2, and I'm sure that later on we can be hearing about progress in the search for that important Higgs decay mode. Another important Higgs decay mode is Higgs into 2 muons. Since the muon is much lighter than the tau, and since the Higgs couplings are expected to be proportional to mass, we expect that Higgs into mu would have a relatively low branching ratio, but it would be very interesting to measure. Also, of course, we would like to measure the Higgs coupling to the top. So we have some indirect indications, but we don't have a direct measurement yet, but this is coming, as you, I'm sure, also hear later on. So some years ago, with my then PhD student, Wong Yu, we asked ourselves the question, okay, the Higgs is supposed to couple to other particles proportional to the mass. What is the evidence for that? Is it possible that the Higgs couplings are not simply proportional to other particles' masses? So we did a very phenomenological fit with couplings of the form mass to the power 1 plus epsilon. As you can see, the fit, shown by these little points with error bars, is extremely consistent with the standard model prediction, totally consistent with the idea that the Higgs couplings are indeed proportional to the masses. Now, that's one of the reasons why we wrote in our paper that this particle walks and quacks like a Higgs boson. Anyway, this type of analysis has been redone more recently by Atlas and CMS in a joint publication in a much more complete and professional way, but again you see that the couplings are indeed consistent with being proportional to the mass. So, as you know, in 2013, the Nobel Prize Committee gave the prize to Peter Higgs and François Englert, and they wrote in their citation that today we believe that beyond any reasonable doubt, it is a Higgs boson. So Tivon and I were very proud because that quotation was actually taken from our paper. That what the Nobel Prize Committee apparently didn't know is that when we sent our paper for publication, the referee told us that beyond any reasonable doubt is not a scientific statement. And we had to take it out of the paper in order to get it published. So this statement was not good enough for the referee, but it's good enough for the Nobel Prize Committee. Okay, So back to our search for physics beyond the standard model. And here I take as my text a movie featuring James Bond with a couple of small modifications. I don't modify this lady here because if you remember the movie, she's a nuclear physicist. Anyway, so the title of the movie was The World Is Not Enough. I argue that the standard model is not enough, and in deference to James Bond, I give you 007 reasons for that. One is this prospective instability of the electric vacuum that I already mentioned. Dark matter, lots more dark matter in the universe than visible matter. We need to explain that. What's the origin of matter itself? This is one of the things that, for example, the LHCb experiment is trying to chase down. Neutrinos, we heard yesterday about the physics of neutrinos, which is not explained within the standard model. The hierarchy of mass scales in physics, cosmological inflation, quantum gravity. I could go on, but I think that 007 is enough reasons to expect physics beyond the standard model. So, experiments at run 2 of the LHC are exploring many of these issues, and I would argue that many of these issues, theoretically, are, if not solved, at least mitigated if there is supersymmetry. So this is why, despite many disappointments, I'm still, perhaps not exactly desperately, but anyway, seeking Susie. So let me say a couple of words about the hierarchy problem, so-called, or if you prefer, the issue of the naturalness of the value of the Higgs mass. So the problem here comes when you calculate quantum effects, and quantum corrections to the mass of the Higgs boson are formally quadratically divergent, which means that it seems very strange that these corrections would cancel out the tree-level value of the Higgs boson mass in such a way as to get a small physical value. And, well, one way of getting that cancellation to work is to postulate supersymmetry, although there are some others. So there are basically 2 points of view. One is the point of view that the Higgs is elementary and probably you have supersymmetry. And then there's what I call the alt-right hypothesis, which is that the Higgs is actually a composite object, much like the pion in QCD. So theorists spent a lot of time constructing such theories. They had a lot of difficulties initially making them compatible with the available precision electroweak data, although that problem has now been largely overcome. And people now think, again, about the possibility that the Higgs is some sort of pion-like object, so-called pseudo-Landau-Goldstone boson. So in order to analyze this possibility, what people propose is a phenomenological framework where you write down a Lagrangian with a bunch of couplings like what you get in the standard model, but with arbitrary coupling modifiers. So written in red here, I have some of those coupling modifiers, A, B, C, and so on. I understand they're normalized in such a way that in the standard model, those modifying factors would be equal to 1. So A is the modifier for the coupling to gauge bosons, and C is the modifier for the coupling to fermions. So the possibility that those modifiers might differ from 1 has been studied by the experiments. Let me just show you a couple of plots referring to that. So, somewhat confusingly, the experiments decided that calling those modifiers A and C is too simple, so they call them kappa, kappa V, and kappa F. Anyway, they're the same thing. So here we have an analysis from the G-Fitter collaboration. So these yellow and orange ellipses are the constraints coming from Higgs measurements of the LHC, and the blue is a combination with precision electroweak data. And I think this plot makes clear the point that it's actually a combination of Higgs data with other data that gives you the most stringent constraints on the standard model or possible deviations. So this compares ATLAS and CMS data with the predictions of some composite Higgs models. So those models have a parameter called zeta, which parameterizes the deviation from the standard model. And what you can see here is that if you make that parameter small, then you get close to the standard model prediction. And that standard model prediction is, unfortunately, in perfect agreement with the experimental data. So this type of analysis will be continuing, but for the moment, there's no indication here of any deviation from the standard model. So theorists have proposed another approach, which is to say, okay, let's suppose that those couplings written down in the Lagrangian on my first slide are precisely correct. Let's allow for the possibility that there are additional couplings corresponding to higher dimensional interactions, which would be scaled by the inverse of some higher mass scale in lambda. Now, if you do this in full generality, there's an enormous number of additional interactions that you can write down, literally thousands of them. However, if you make some simplifying assumptions and restrict yourself to the data on the Higgs boson and related phenomena, then there's actually relatively few interactions that are actually relevant. So the interactions which it's interesting to use in a fit to these parameters are, in addition to the Higgs data, the precision electroweak data, and data on triple gauge couplings. So these plots show you how the precision electroweak data taken at LEP and the SLC in the 1990s, how they constrain some of these higher dimensional operators. It's probably not easy to make it out, but typically what they're doing is they're telling you that these additional interactions must have scales lambda, which are bigger than several TeV in some cases. So this is an analysis that we did where we include Higgs data. So the blue bars correspond to the constraints from associated Higgs production. Red constraints adding in triple gauge couplings. Black is a global combination. And you see, well, for these particular operators here that contribute to Higgs production, the constraint on lambda is approaching a TeV, but not yet exceeding it. So again, no evidence yet for physics beyond the standard model, although the experiments are probing the TeV scale. And I'd just like to emphasize again that this type of analysis uses both Higgs data and other LHC data. And this is another analysis that exemplifies that. So here in green, we have the constraints coming from Higgs data. In orange, we have the data from triple gauge coupling measurements, and you put the two together, and you get this little blue ellipse here. So this sort of global analysis, I think, is the way forward for the future. And in fact, the Atlas collaboration has just published just such a global analysis. Maybe we'll be hearing about it in a moment. Okay, so I've given you lots of reasons for thinking that there should surely be physics beyond the standard model. So what might that physics be? So a lot of people take very seriously this hierarchy problem, the problem of the mass scale of the Higgs boson. As you can see, there's various different theoretical responses to that problem. This slide I stole from Nathaniel Craig. Of course, some people say that it's not a problem. They say, well, you just put the Higgs mass to be whatever you want and you just carry on. Personally, I find that very unsatisfactory, and that's why I've been discussing various alternatives over here. I discussed composite Higgs, I'll be discussing supersymmetry, some of these other options I won't discuss. But I should also mention that there are some people who say, well, okay, we have to have the value of the Higgs mass that we have for purely anthropic reasons. things are the way they are because they have to be that way. I personally detest that type of argument. I think it's a scientific cop-out. So, just in case it wasn't clear already, my own preferred scenario for physics beyond the standard model is supersymmetry. And my way of thinking about that at the moment is summarized in this cartoon from the First World War. So here are a couple of guys stuck in a hole, okay, and they're being bombarded with all sorts of negative experimental results, not finding evidence for physics, new physics beyond the standard model at the LHC. In particular, no evidence for supersymmetry, but one of them says to the other, if you know of a better hole, go to it. So that's all the way I feel about supersymmetry. If you knew of a better theory, then go to it, but I don't, so I'm sticking with supersymmetry. So here we are, supersymmetry written in big letters, the biggest that will fit on the slide. And I would actually argue that round one of the LHC actually produced 3 additional reasons for liking supersymmetry. As I already mentioned, supersymmetry can stabilize the electroweak vacuum. It made a successful prediction from the mass of the Higgs boson. It predicted that the couplings will be similar to those in the standard model, which they are. And all that is in addition to all the other reasons, such as the hierarchy problem, dark matter, and so on. So maybe I don't need to say very much about the structure of supersymmetric theories, but perhaps to remind you that according to supersymmetry, all the known particles are accompanied by partners which have identical quantum numbers, except they have different spins. So the experiments have been looking for these and haven't found them. Of course, I haven't found anything else either. So, some supersymmetry theorists are a little bit depressed. I think the absence of direct evidence for physics beyond the standard model at the LHC is certainly a big challenge for us theorists, and I think we should be thinking together with the experimentalists about how to continue the search for new physics at the LHC. Should we be pursuing the same search strategies that we've been following up to now, or should we be looking for new unexplored signatures? Anyway, to come back to supersymmetry, one of the complications in looking for supersymmetry and understanding the experimental results is that there are many different supersymmetric models. This is another slide that I stole from Nathaniel Craig, and I think the take-home from this slide is that there are no signposts in superspace. We should consider all possible options for the way in which supersymmetry might appear. So, this is what I do together with a group called the Mastercode Collaboration. So what we do is we incorporate all the available experimental constraints on physics beyond the standard model, coming from precision electroweak data, coming from flavor observables, coming from constraints on dark matter and its scattering, and coming, of course, from measurements at the LHC. So I might mention that there are a couple of possible indications that there is something beyond the standard model. So one of them is the anomalous magnetic moment of the muon, which shows a discrepancy between the experimental measurement and theoretical calculations within the standard model, a discrepancy that could be explained by supersymmetry. And then there are also issues with various flavor observables that we'll be hearing about tomorrow, which personally I would find rather difficult to explain within supersymmetry, but maybe some other theory. Okay, so this plot is taken from the most recent phenomenological analysis of supersymmetry that we did, and here I just show you the best fit supersymmetric spectrum that we find in our fit to this phenomenological supersymmetric model. The main take-home from this slide is that there are still significant prospects for discovering supersymmetry in future runs of the LHC. In this and many other models, you can have supersymmetric quarks which weigh less than 3 TeV, which should be accessible to the LHC experiments as the luminosity is increased. Now, as I mentioned, perhaps in addition to just the sort of traditional searches for supersymmetry, we should also consider looking for other signatures. And this is an example. So in this phenomenological model, there are significant possibilities for finding long-lived particles. In fact, supersymmetric models could accommodate particles with lifetimes as long as 1,000 seconds. And of course, experiments are looking for such long-lived particles, well, so far, no luck. I should also mention that although I don't think that the flavor anomalies that have been reported recently by LHCb are easy to explain within supersymmetry, there is one measurement which I find very interesting, which is the measurement of Bs goes to mu plus mu minus, which even in the supersymmetric models that we've been studying could exhibit a significant deviation from the standard model prediction. Now, I've talked a lot about searches at the LHC. Of course, that's not the only place where you could look for physics beyond the standard model. In particular, I'm interested in searches for dark matter particles. So in this slide here, you show a sort of panorama of the sensitivities of different experiments to the direct scattering of dark matter particles. So these are the experimental limits here. Down at the bottom we have the neutrino floor, which you heard about yesterday. And in pink here we have a sort of region which is supposed to indicate the possible range of predictions of supersymmetric models for this direct dark matter scattering cross-section. So you see that there are significant possibilities that the dark matter scattering cross-section might be close to the current experimental upper limit and above the neutrino floor, and hence potentially accessible to experiments. So this plot is taken again from our most recent analysis. So this is the best fit point here, and you see this lies in the region where the cross-section is smaller than the current experimental upper limit, but potentially larger than the neutrino floor, and hence accessible. So that plot was for spin-independent dark matter scattering. We did a similar analysis of spin-dependent dark matter scattering. I kept this in because I know there's at least one person who is interested in spin-dependent dark matter scattering in the audience. And here is a comparison of our predictions with the current upper limit given by the PICO experiment. So I don't have time to discuss these other flavor anomalies. I expect you'll be hearing more about them tomorrow. As I already mentioned, these don't, for me, fit very naturally within a sort of supersymmetric framework. So I'll just skip over this because I'm running out of time. Okay, so in the last 2.5 minutes, I just want to discuss the longer-term future. So the LHC is expected to continue to run for perhaps another 20 years, and it eventually will accumulate something like 100 times more data than what has been analyzed so far, up to something like 3,000 inverse femtoruns of data. But of course, people are already thinking about what collider they would like to build after the LHC, because these things take a long time to come to fruition. And so one of the options that's being considered is a future E plus E minus collider. And here there are various ideas on the market. One of them is a large circular collider. This is being studied both at CERN and in China. This would give you a relatively limited centre of mass energy, but potentially a very high luminosity. Another possibility is a device called a click, which would go to higher energies, although at low energies you would have a smaller luminosity. And then you also have the ILC, which has been proposed in Japan, which personally I don't find so interesting because it's limited in both luminosity and central mass energy. So this is an image of where a large circular collider might be located around Geneva. Here is the city of Geneva, here is the Jet d'Eau, and here is the track of that collider going around the mountains there. So in such a large circular ring, you could collide protons at energies up to 100 TeV in the centre of mass, and that would enable you to explore directly physics at the 10 TeV scale, as well as make indirect probes by doing E plus E minus collisions in the same tunnel. So this is a picture that we did showing how accurately the Higgs coupling should be measured. So I don't know whether you can make it out, but there are infinitesimal little dots here that represent the accuracy with which Higgs couplings can be measured at a future large circular E plus E minus collider. Of course, the proton-proton ring would also produce lots and lots of Higgs bosons and thereby give you the potential for precise Higgs measurements, although that full potential has not yet been analysed in great detail. But you can see here that going from 13 TeV to 100 TeV, these cross-sections increase by over an order of magnitude, in some cases almost 2 orders of magnitude, and also for the first time this will give you access to a direct measurement of the Higgs self-coupling. And of course, in addition to those gazillions of Higgs bosons, you would also produce heavy particles weighing up to 10, 15 TeV or more. So, to summarize, the discovery of the Higgs boson at the LHC has been, on the one hand, a great victory for theoretical physics as well as experiments, but it's also a tremendous challenge for theoretical physics to understand this particle and to use it as a probe for possible physics beyond the standard model. Now, the LHC may still discover physics beyond the standard model, and if it does, surely the priority for the future will be to study it. If it doesn't discover new physics beyond the standard model, then it would be natural in the future to do experiments to focus and measure as well as possible the properties of the Higgs boson. In either scenario, I personally believe that a large circular collider is the most powerful instrument for future discovery. Thank you.